And for me, it's a pleasure to introduce Tania Lepivert. Tania is our new postdoc in the solar system group of the IAC. She's been working at Paris-Eclair University with Dr. Rosario Brunetto, one of the world experts in laboratory analysis of asteroid material and materials that can be found in asteroids, Transneptunian comets, and so on. Tania finished her PhD thesis late last year, December last year, working in the analysis of meteorite samples and in the analysis of particles brought from one of the missions that visited an asteroid, took a piece of asteroid and bring this sample to Earth, the asteroid Ryugu from the Hayabusa 2 mission. And she's also having access to material from another asteroid, Bennu, that was a sample return mission by NASA called OSIRIS-Rex. So she has in her hands one of the most primitive and most valuable material we have on the solar system, as it probably will explain. The material she is analyzing is likely millions or 1,000 million years, 2,000 or 3,000 million years old, and was almost not processed or very little processed in the origin of the solar system. So I think that I talk too much. I let her explain what she's doing. Thank you, Tania. Oh.
Okay, does it work? Yeah, perfect. So thanks for the introduction, Javier. So yeah, as Javier explained, I'm a planetary scientist interested in the study of primitive small bodies in the solar system. And in my past research, I had the opportunity to work on sample return mission about primitive asteroids. So today I will present you some very interesting results about sample return mission and why they are so important to understand the story of the solar system. Okay, but first, we need a little bit of context. So asteroids are small bodies in our solar system. The main reservoir of asteroids is the asteroid main belt, located between the orbits of Mars and Jupiter. And this belt contains a lot of asteroids. We estimate the number of objects with a diameter larger than 1 kilometer to be between 1 and 2 millions. But that does not represent that much in terms of mass. Asteroids have very various sizes and shapes, the largest one being Ceres. And this variety of shapes and sizes is partly linked to a complex collisional history. We believe that the first object formed in the solar system, the planetesimals, were born big, but then due to collisions, the fragments reaccreted into smaller and smaller objects. Also, the asteroids exhibit various colors and spectra, which we think is partly related to their composition. And so to understand all the variety of composition of the asteroids, we made what we call taxonomies, which basically means groups of similar spectra. And then to understand what does each group means in terms of composition, what we usually do is that we compare the spectra of the asteroids with spectra of meteorites. So meteorites are fragments of asteroids that fall on Earth, which is very interesting because we can analyze those samples in laboratory with a lot of techniques to understand what is the mineralogical composition, the isotopic composition, for example, and it helps us to constrain the composition of the asteroids. So far, we made a great job by understand the links between spectra of asteroids and meteorites. For example, the V-type asteroids, which are related to the asteroid Vesta, we found some links with some meteorites called the HED. Also, the S-type asteroids are believed to be linked with ordinary chondrites, and we really understood that thanks to a sample return mission named Hayabusa. So this mission collected samples from an S-type asteroid, bring them back to Earth, and by comparing the sample of the asteroids and the ordinary chondrites, we were completely sure that the two objects were very similar. And then you also have the C-type complex here. These asteroids are very dark. We believe they contain organics, and we think that they're related to carbonaceous chondrites, which are a type of meteorites containing organics, basically. But there are many subclasses of C-type asteroids and many subclasses of carbonaceous chondrites, and for the moment, we don't really know the link between the different subclasses. And carbonaceous chondrites are very interesting because we find them today in the asteroid main belt, but we think that they were not formed here. We think that the carbonaceous planetesimals formed very far away in the solar system, possibly beyond the orbit of Jupiter. And at these distances, the temperature was low enough to enable the condensation of H2O ice and other volatile phases. And so the body formed at these distances accreted ices and volatiles. So by studying the carbonaceous planetesimals, we study, in fact, the distribution of volatile phases in the primitive solar system, especially because those bodies here, the rocky planetesimals, did not accreted the ices and the volatile phases. But as I said, there were dynamical evolution in the primitive solar system. And we think that because of the growth of the giant planets, there were some instabilities in the primitive solar system. And some of the objects from far away were implanted in the main belts. So now when we study asteroids, primitive asteroids in the main belt, the question we aim at understanding is, okay, where do they form originally? Also, in addition to dynamical evolution, the asteroids underwent compositional evolution because they accreted some radioisotopes. And by the heating of the radioisotopes, this heating changed the composition. So when the heating was very important, it could lead to the differentiation, which means that the heavier elements migrated towards the center of the object. So to access the primitive composition of the solar system, we must focus on the undifferentiated ones because they are more similar to the primitive, they're less evolved in a way. But still, even if the evolution was less important, the temperature for some of these bodies were important enough to allow the melt of the ices. And these ices reacted with the anhydrous minerals to form secondary phases, hydrated phases, like phyllosilicates or carbonates. And this process that we call aqueous alteration, we need to understand it for two main reasons. First, we want to understand what was the initial composition of the parent body. And then we think that some of the carbonaceous planetesimals could have brought some volatile phases in the inner solar system in the past, especially on Earth. So we want to know all the evolution of the volatile phases and the organics before its possible supply to the inner solar system. And finally, today, there are other effects that modifies the compositions of asteroids. One of them is space weathering. So space weathering combines different effects: the bombardment by micrometeorites, the irradiation by the solar winds, and by cosmic rays. And it affects the structure and the composition of the first layers of the surface. As we can see here on an Itokawa particle, only a few nanometers are affected, but this is enough to modify the spectra of the asteroids, which is our main tool to access the composition, actually. So thanks to the lunar sample return mission and also the Hayabusa mission, we understood how space weathering modifies the structure, the composition, and the spectra of asteroids. Especially, we can see here a comparison between an ordinary chondrite and Itokawa, and it shows that the slope, the level of reflectance, and the depth of the bands varies. But for carbonaceous asteroids, we don't really know what are the effects. And so for all these reasons, we need the sample return mission. First, from the spectra of asteroids, we only have a limited information and they can be biased by space weathering. And studying carbonaceous chondrites is not enough because we don't have all the context. We don't know from which parent body they originate. Plus, we think that some of the chondrites can undergo some terrestrial alteration processes. So that's why in the 2010s, two space missions, two sample return missions were launched towards primitive asteroids, the Hayabusa 2 mission from JAXA and the OSIRIS-Rex mission from NASA. So in this presentation, I will only focus on the Hayabusa 2 mission because the samples from OSIRIS-Rex returned to Earth very recently, last September. Okay, so the target of the Hayabusa 2 mission is Ryugu, this asteroid here. It's a carbonaceous asteroid. It's very dark, and its relative small size and high porosity can be explained by the fact that Ryugu is a rubble pile asteroid, which means that its parent body, which was probably in the main belt, once experience fragmentation due to collision with other objects, and part of the fragments reaccreted to form Ryugu. And now Ryugu is located in the near-Earth asteroid region. It's moved from the main belts, and this is very convenient if we want to get there, collect samples, and bring them back to Earth. So yeah, during 2 years, the Hayabusa 2 spacecraft studied the surface of Ryugu, and we understood we discovered a lot of interesting things about this object. For example, the NIR3 spectrometer detected a feature here at 2.7 micron. And this absorption band is similar to the one we can see in carbonaceous chondrites that underwent aqueous alteration. So only by comparing the two, we can say, okay, maybe Ryugu experienced some aqueous alteration. This is very likely. But contrarily to carbonaceous chondrites, the feature in Ryugu is very weak. The band depth is very weak, and it looks more like chondrites that would have been heated or that would have undergone some shocks. So then, after characterizing the surface, the spacecraft collected samples 2 times. You have here the 2 collection sites. And you have here a small videos showing the process of collection of the samples. And what is very interesting with the Hayabusa 2 mission is that the second collection site was made in an artificial crater. So basically, the spacecraft dropped an artificial impactor at the surface. It created a crater. And then the spacecraft collected samples in the ejecta of the crater. And so these samples in the ejecta, they originate from the subsurface of the object. So by comparing the 2 collection sites, the surface and the subsurface, it will provide a lot of information on the evolution of surface, especially due to space weathering, for example. Then the sample came back to us in December 2020. So you have here a nice photo of the container, the capsule return. And you have here some photos of the retrieving of the capsule. It landed in the Woomera Desert in Australia. And what is very important is that the container with the sample was hermetically sealed in order to avoid any terrestrial contamination of the samples when it comes back to Earth. Then the capsule was transferred into the ISA's Curation Facility in Sagamihara in Japan. And you have here a photo of the Curation Facility. So it's a complex of clean rooms that are built to store the samples and to analyze them without any contamination by the terrestrial atmosphere again. And on the right, you have here the complete collection of Ryugu samples. So all the samples from the first collection sites are here. I will call that chamber A. And you have also the chamber C, the second collection sites over there. And then what happened after the samples were there? In the curation facility, the initial description phase began. So the idea of the initial description phase is to characterize all the collection, all the grains, with only non-destructive techniques and without exposing them to the atmosphere. So this phase is actually still going currently because we have a lot of samples. And then some of the samples were extracted and distributed to 6 international teams. And these teams used a wider range of techniques to study different aspects of the composition of Ryugu to understand its history. But some of the techniques are destructive, so of course they cannot be applied to all the collection. And since 2022, the JAXA opened the announcement of opportunity to request some samples. So anyone in the world can write a proposal, request for a grain. But again, we can use all the techniques we want, but on a limited number of samples. And to select which grain is very interesting for a specific study, the initial description in the curation facility have built a catalog. So in this catalog, you have many information on the grain, including some spectra. Because in the curation facility, there is different instruments that perform some spectroscopy of the grain. And one of them is called micromega. It's the metallic box you can see here. So micromega is an hyperspectral microscope operating in the near infrared range. And it basically takes pictures of the grain at different wavelengths, as we can see here. And then by stacking the pictures, we obtain hyperspectral cubes. So for each pixel of the image, we have access to the spectra, which is interesting because we can study the spectra of the grains and the spectral variations at the surface. You have an example here of a grain. It's a composite image taken with 3 different wavelengths, and we can see that this region have a different spectra from the rest of the grain. And so what is the aim of all that? The goal of the mission of all the analysis in the curation facility by the initial analysis and so on is to understand the evolution processes that occurred on Ryugu and its parent body since its formation. Also, it's important to understand the spatial and time scale of all the evolutionary processes. And what we can do in the curation facility with micromega to answer this very big question is to study the spectral variation of the samples at different scales. And to really understand the full story, we need to do links with the remote sensing observation of the surface, but also with all the results obtained with different techniques by the initial analysis or the announcement of opportunities at smaller scales. And so I will present you some results about that work, about the spectral variation obtained at 2 different scales, the millimeter scale and the sub-millimeter scale. And I will also present a comparison between the samples of Ryugu and the carbonaceous chondrites. But first, I need to go back a little bit in time because the very first measurements made in the curation facility by micromega were measurements on the bulk samples. So what I mean by bulk samples is all the grains in the same sample holder like this. And the instruments measured all the field of view. And we have here the average spectrum of the 2 chambers. And from this, we can already have some interesting information. For example, here at 3.4 micron, we detect an absorption band, which is due to the presence of organics, but also carbonates. We have at 3.1 micron another absorption band, which we believe is related to NH-rich compounds. And we also observe an absorption band at 2.7 micron, which was the band observed at the surface of Ryugu. And this band is due to the stretching vibration of OH in the structure of phyllosilicates. So the OH is bound to a metallic atom in the phyllosilicates. And this band, actually, it characterizes the most abundant minerals in Ryugu sample, which are the phyllosilicates. Also, we believe that the position, I mean, many studies on chondrites showed that the position of this band is related to the composition of the meteorites or the composition of the phyllosilicates, and is also related to the degree of aqueous alteration. Here you have an example of different meteorites with position at different wavelengths, and the more Mg-rich meteorites have peak position at shorter wavelengths. And in our samples, we see a peak position around 2.716 micron, which is very similar to the position observed in the CI-type chondrites, which means that the sample contains Mg-rich phyllosilicates. And when we compare the two chambers with those two normalized spectra, what we see is that the position is very similar between the two chambers. So at the centimeter scale, we don't see really compositional variations between the two collection sites. So we need to go to a smaller scale to try to detect this. So in the Curation Facility, after the bulk were measured, the grains were extracted individually, one by one, put into sample holder, and analyzed by many instruments, including micromega. And the idea here to study the composition at millimeter scale is to obtain an average spectrum of the grain by averaging all the pixels in the micromega hyperspectral data. And we have here an average spectrum for each grain. So the idea is also to do that for a large number of grains to do a statistical study. So here I will show you an analysis of 200 grains, which basically represent 20% of the mass of the collection. So at first order, it's representative. Okay, so when we compare the grains one by one, we can see some spectral variations. Here you have two normalized spectra of two grains, so don't pay too much attention to the y-axis. But what we can see is that the position of the band varies between the two grains. And also we can see variations in the band depth of the feature. You have here an example of two other grains that have a very similar level of reflectance, but different band depth. Okay, and so what happened when we look at all the 200 grains? We obtain this kind of figure here. So you have the dispersion graph between the band depth and the peak position of the 2.7 micron feature, and each dot represents a grain. The red ones are from the chamber A and the blue ones from chamber C. So here we see a spectral heterogeneity between the grains and between the chambers. Especially, we can see two populations. A first one that I will call blue shifted grains, which are grains with peak position at short wavelengths and band depth varying between 8 and 23%. And we could subdivide actually this population in two, because we can observe over there some grains from chamber A that have a higher band depth and the peak position slightly shifted toward shorter wavelengths. And then we have a second population that I will call redshifted grains, which have peak position towards longer wavelengths and low value of band depths. And what is very interesting is that the redshifted grains are mostly from chamber A. There is very few grains from chamber C in this population. So as you may know, the variation we see in the peak position means that there is a variation in the composition between the grains. And especially by comparing with what we see in phyllosilicates and in chondrites, we know that those grains here, the redshifted grains, have a more Fe-rich population, a more iron-rich population than this population. And so now, okay, we see some variation in the composition, but why do we see that? And so we investigate in many scenarios, and one of them could be that different degrees of space weathering provoked this variation, because there were some experiments of space weathering on materials that are analogs to carbonaceous asteroids, like phyllosilicates or carbonaceous chondrites. And these experiments showed that space weathering can affect the composition and the structure of the phyllosilicates. For example, an experiment showed that the irradiation leads to a dehydroxylation, so a removing of the OH bonds, which produce a decrease of the 2.7 micron band depth. And you have another experiment here from Rubino et al. That shows that the irradiation can also provoke preferential sputtering of magnesium compared to iron, or a preferential amorphization of Mg-rich phyllosilicates. And this leads to a variation of the peak position, a shift of the peak position towards longer wavelengths. Okay, so we know that space weathering can cause variation. So the question we can ask is, does variation in the degrees of space weathering in the grains explain the variation we see in the peak position and the band depth in Ryugu grains? And so for that, we need to focus on other studies, especially with the electron microscopy. Some teams detected textures associated with space weathering, such as circular structures, melt droplets, and smooth and frosty layers. And what is interesting in one of these studies, the study from Nakato et al., is that they discovered one grain where there is an area here which contains very few textures associated with space weathering, and another one which contains more textures associated with space weathering. And when they looked at the composition of the two regions, they saw that the space weathering rich area, which is in red here in this diagram, shows more variety in composition, and especially some spots on the surface have a more iron-rich composition than the space weathering poor area, which is in black here on this diagram. And this variation in composition is completely consistent with the spectra obtained by Micromega. So you have here the average spectra of the two regions, and the space weathering rich area in gray is shifted toward longer wavelengths towards a more iron-rich compositions. And this, so this hypothesis that space weathering produced the variation we can see here is totally consistent with all the observation made at the surface of Ryugu. So you have, for example, here a study from Kitazato et al. They compared the spectra of the subsurface with the spectra of the surface. So they made ratio between the spectra of the artificial crater in blue, the spectra of the ejecta of the crater in green. They divided those spectra by a typical spectra of Ryugu's surface. And you have here the ratio. And you see a feature over there that means that the subsurface spectra have deeper band depth and peak position shifted toward shorter wavelengths. And the more recent study estimate the shift between the subsurface and the surface to around 6 nanometers, which is consistent with what we see between the two populations. Okay, so to summary the result I showed you here, at millimeter scale, we see some compositional variations between the grains and between the chambers. And it looks like space weathering could explain those variations. So thanks to that, we can understand that on carbonaceous asteroids, at least on Ryugu, the space weathering provoke a diminution, a decrease of the band depth, and a shift towards longer wavelengths. Also, it means that the grains from chamber A that were collected at the surface, they both are very exposed. In chamber A, sorry, they are grains that were very exposed and grains that experience weak exposure. So maybe those grains here were initially in the volume of the grains, so they were protected from space environments, but due to the collection process, there was some fragmentation, and then the surface of those interior parts was exposed. And the second result is that the chamber C, the collection at the subsurface, only contain only grains with weak exposure to space weathering. So that means that there is no mixing, vertical mixing between the layers at the surface of Ryugu, at least where there was the collection sites. And when a grain is at the surface and experience space weathering, it's not buried by other grains after that. Maybe due to the low gravity of Ryugu, it's ejected in space or at higher latitudes. Okay, so we understood a bit what were the compositional variations at millimeter scale, but with micromega, we can study them at smaller scale. And that is very interesting because the most abundant minerals detected in Ryugu are all minerals formed by aqueous alteration at low temperature, like the phyllosilicates and the carbonates. But when you look at smaller scale, we can see that Ryugu grains are very heterogeneous. They consist of fragments with different composition. And these variations, some of the variation in composition are related to difference in the degree of aqueous alteration. So you have here an example of a false color map obtained with near infrared spectroscopy. And this shows some regions that have a different composition here. And when you look at the spectra of this class, you can recognize some signatures of anhydrous minerals like olivine, pyroxene, amorphous silicates. So this class may have undergone a less degree of aqueous alteration. They were less altered. But this is obtained for one grain. And in the Curation Facility, we can analyze all the collections. So the question is, okay, can we find those kind of variations in other grains? So this time we won't do an average spectrum of the grain, but the idea is to study the spectral variation at the surface by comparing all the different pixels at the surface of the grain. And when we do that, for the 2.7 micron feature, we see that some of the grain are very homogeneous. The position is very similar on all the surface. And some of them are very heterogeneous, but at a very small scale, at the pixel scale. And in a small fraction of the samples, we can see what I will call large-scale heterogeneities. So that's spectral heterogeneities at scale between 500 microns and up to 1.5 millimeter. And this is an example of what I mean by large-scale heterogeneities. So you have here two maps of spectral parameters, the map of the peak position of the 2.7 micron band and the map of the band depth of the feature. And we can see two regions here and there where the peak position is shifted towards longer wavelengths and the band depth is weaker than the rest of the grain. And what is interesting in those two examples is that the heterogeneity, the large-scale heterogeneity, seems to be related to a variation of the surface aspects when we look at the microscope images. So in this example, we can see variation in the peak position of the band. So that could mean there are some variations in the composition of the phyllosilicates, and maybe it is related to different degrees of aqueous alteration. But sometimes, like on this example, we don't really see variation in the peak position here, but only a variation in band depth. Here we have a small region with band depth that are weaker than the rest of the grain. And again, it's related to a region here, which is a little bit brighter on the microscopic image. So in that case, maybe we don't observe variation in the composition, but maybe it's variation in the abundance of other phases, like opaque phases, like sulfides or magnetites that have been detected on Ryugu grains. So yeah, there is a lot of things to understand with the small-scale heterogeneities, but it is important because some of the heterogeneities we detect could be related to lithologies with different degrees of aqueous alteration. And I will show you another small example. So with micromega, we detected some carbonates also. We can detect them thanks to this huge absorption band at 3.4 micron. And when we do a statistical study of carbonates in all the grains, we can see that the two major carbonates we observe are dolomite and brunnerite, with dolomite being the largest detections. And what is interesting is that we don't see spatial transition from one mineral to another. And we don't exactly know why there are no transition. Maybe that could mean that the two minerals form separately, possibly during different episodes of aqueous alteration. So yeah, to summarize that, at small scale, at some millimeter scale, we see some variation in the spectral parameters at the surface of the grain. And some of the variation we detect could be related to different degrees of aqueous alteration. So we need to study that in more depth, but it's very important because it provides information on what was the original composition of the parent body, and also at which scales the aqueous alteration start to be an heterogeneous process. Because as you remember, when you look at the surface of Ryugu or when you look at the bulk, the 2.7 micron doesn't vary, which means that the composition is homogeneous. And at smaller scale, it starts to be very heterogeneous. So why exactly? We don't know. Okay, so that was all for the spectral variation. I will just finish with a comparison between Ryugu samples and the carbonaceous chondrites. So all the analysis in the Curation Facility and by the initial analysis team showed that the best meteorites analog to Ryugu samples in terms of compositional, elemental, organic, and isotopic composition are the CI chondrites, which are carbonaceous chondrites that experience aqueous alteration at low temperature. And you have an example here of the elemental abundance of two Ryugu particles normalized to the elemental abundance of CI chondrites. And we can see that for a lot of elements, the abundance are very similar. But similar doesn't mean identical. And in fact, we see some differences between Ryugu and the CI chondrites, especially in their spectra. You have here a spectra of CI chondrite orgueil and two Ryugu grains in blue and red. And what we see is that there are some differences. First, the level of reflectance is not the same, and we believe it's due to the presence of sulfates in orgueil, the CI chondrites. And we were a little bit suspicious about the sulfates. We believe that it could be a product of terrestrial contamination in the CI chondrites. But now with Ryugu sample, we have the final evidence because we did not detect any sulfates in the sample of Ryugu. The other difference we see is in the shape of the 3 micron feature over there. So we know that when we measure meteorites in ambient conditions, some water of the atmosphere can be adsorbed at the surface of the meteorites over there. So what we usually do is that we measure the meteorite in an environment where we heat the environment at 100, 200 degrees to remove this adsorbed water. And indeed, it decreases a lot the feature here at 3 micron, which is related to the absorption of water. But is it enough? The answer is not totally. When you compare the spectra of the heated CI chondrites and Ryugu, you can still see a difference here in the depth of the 3 micron feature. And so it means that there is still more water in the heated chondrites, and if it's not adsorbed water, it's probably structural water, which means water inside the minerals of Ryugu. For example, we know that some of the phyllosilicates, which are minerals organized in layers, some of the interlayer space are wide enough for molecules, for water molecules to go inside. So this variation in the spectra means that Ryugu contain less structural water and adsorbed water than CI chondrites. And this is also consistent with other analyses like thermogravimetric analysis which basically means that you eat the sample and you look at what species is degazed at what temperature. And here, the author of this study identified a peak due to the interlayer water, and they show that Ryugu grains contain less interlayer water than the CI chondrites. And so what does that mean? Why is there less water in Ryugu than CI chondrites? Well, because Ryugu and CI chondrites have a very similar composition, maybe it could mean that Ryugu in his past history experienced some heating, but this is a very unlikely scenario because there are a lot of volatile phases in Ryugu sample. We detected organics and H-rich compounds. So the more likely scenario is that the water in the CI chondrites, the structural water, comes from terrestrial contamination. Okay, and to summarize that, we see some difference between Ryugu samples and the carbonaceous chondrites, and part of these differences can be explained by terrestrial contamination. And this is interesting because we can understand how terrestrial contamination affects the composition and the spectra of carbonaceous chondrites. And this is also very important because before the sample return mission, we used the CI chondrites as a reference to estimate the elemental abundance of volatile phases in the solar system. But now we have a better reference because Ryugu samples are not contaminated. And so, yeah, to conclude this presentation, I hope I convinced you that sample return missions are really essential to understand the complex history of carbonaceous asteroids. First, because it provides pristine samples preserved from terrestrial contamination. And then because by doing different analysis at different scales with different techniques, we will have a better understanding of all the evolutionary processes that affected the carbonaceous asteroids. And that ends my presentation. So thank you, and I will be happy to answer any questions.
Thank you, Tania, for this super interesting talk. Are there any questions in the room?
Okay. Oh, so first, thank you for the talk. It was very interesting. I have two questions. One is about the terrestrial contamination in the meteorites. The terrestrial contamination happens when the meteorite is trespassing the atmosphere when falling, or is because weathering in the surface after time you discover the...
It's mostly when it's at the surface. For example, for almost all the carbonaceous chondrites we did not find them just after the fall. We find them after many years. And then when we obtain the meteorites, it can stay in a museum for many, many, many years without very good preservation. So that can explain why the carbonaceous chondrites are subject to terrestrial contamination. Also, the composition will be an important aspect. Carbonaceous chondrites, because they contain volatile phases, organics, maybe they are more subject to terrestrial contamination than other type of meteorites that contains only silicates, for example.
Okay, and the other question is about the all the processes has been described, and also the minerals that you find in the samples of the asteroid are the same that you can find in the igneous rocks on Earth. So are you working or collaborating in any case to compare your asteroid samples not only with meteorites or chondrites, but with igneous rocks or different kind of igneous rock that probably can help in understanding different processes that lead to the actual composition of the asteroid also?
Well, it helps for sure to do some comparison between terrestrial minerals and materials from asteroids. The problem is it's not the best analogs because the formation process are different. And just to give you an example with phyllosilicates, all the phyllosilicates we have on Earth, they all contain water in their interlayer space. So you will always see when you measure phyllosilicates from Earth, a huge 3-micron band, which is not the case for the phyllosilicates in carbonaceous asteroids. So it can help, but the story of formation is different. So we cannot do that. We cannot do all the science with only comparing Earth minerals and minerals from Ryugu, for example.
Okay, thank you very much.
Hi, Tania. Thank you. It's amazing that you work on this issue. It's very new and very fine. I have a question about the change in a slope in the near infrared between the two chambers.
Yes.
Yeah.
I can go back on that, maybe. Here.
Yep, this. So I was thinking, because the main thing that differentiates the two chambers, we saw that is space weathering, right?
Yes. It depends at which scale you look. Yeah.
Okay. So this change in slopes has something to do also with the space weathering, or is not?
I'm not sure, because when maybe I should go back to this figure. So I looked at several spectral parameters, including the spectral slope. And when you do this kind of dispersion graph with the spectral slope and the peak position, you don't see like any particular correlation. So maybe the spectral slope changes with space weathering, but what I think is that there are so many effects that can affect the spectral slope that it will not be very visible in our data. Especially the grains we measure, it's like real grains, it's not powders. So you can have a lot of photometric effects that changes the slope, and maybe it affects less the band depth and the peak position. So that's why these two parameters are better to characterize space weathering in our measurements. Of course, if you like do a powder of the sample, maybe the spectral slope will be very interesting then to compare different exposure to space weathering. Yeah.
Okay. Sounds interesting, and we found something similar, maybe also in the near ultraviolet. Let's see. Thank you.
So I think we have a question online. Yeah, please, Julia, you can go ahead.
Can I speak? I mean, can you hear me?
Yeah.
Okay, thanks. Thank you, Tania. This is an excellent work. I'm still amazed at about all that you can get from just so tiny grains from the surface of Ryugu. It's more a curiosity than a question. As you know, we have samples from another primitive asteroid, Bennu, on the OSIRIS-Rex mission. They arrived a little bit later. They arrived last year. And I know that they are still doing the analysis, but do you have any news, any updates on what they are finding from these grains?
Moment now, the Japanese colleagues from JAXA will receive some grains of Bennu. So they already built another chamber because they do not want to mix Ryugu grains and Bennu grains. And the micromega instrument they use in the Curation Facility for Hayabusa 2 will be transferred to the OSIRIS-Rex Curation Facility. So with the same instruments, we will have comparison between the samples, but the samples are not here yet. They should arrive late August or something like that. But there is some measurement, some spectral of the grains were already measured by the American teams. And what they show for the moment is that the spectra of Bennu are very, very similar to the spectra of Ryugu, in particular in the 3-micron band, which is not very expected because I don't have the spectra here, but when we look at the spectra of the surface of Bennu measured by their instrument, the OVIS instruments, and the spectra of Ryugu measured by the NIR3 instruments, they are totally different. We could say, okay, they have different composition. But when you look at the samples, you obtain the exact same spectra. And for the moment, it's an open question. We don't know. We don't know why there are such differences between the analysis, the remote sensing analysis and the sample analysis. So yeah, we have to work on that for sure.
Will you have access to the samples, to the Bennu samples?
The Bennu samples, some of them will be sent to the Japanese colleagues, a few milligrams, if I remember. So yeah, we will have access to those samples, and it will be very interesting to compare them. Yeah.
Okay, thanks. Thank you very much.
Also, the American teams will also release very soon the equivalent of the announcement of opportunity. So anyone in the world can request for grains and do a comparison with all the techniques we have in the lab, like electron microscopy and so on, between Ryugu and Bennu. So yeah.
Perfect. Thank you.
You've been analyzing in the micrometer scale, and how do you compare with what we know in the kilometers scale? I mean, and we have some, not many, because the 2.7 micron band is you can do it from Earth, but there are some space spectra of asteroids in this region. And well, we will soon have a spectra from James WST. You will be involved in this. Did you try to make any comparison yet, or are you planning to work on this?
Yes, I am working on that. Because the idea is that, okay, at small scale in Ryugu, we see a lot of heterogeneities, but when you go to larger scale, it starts to become very homogeneous. So we could expect that other asteroids are also very homogeneous at larger scale. But what is interesting is that when you look at Ryugu at small scale, you can see different degrees of aqueous alteration, for example. So if another asteroid have undergone a different degree of aqueous alteration than Ryugu, maybe you can still use Ryugu particles to do some comparison between the small scale and the large scale. So that's something I am trying to do at the moment, to look that if we cannot obtain primitive lithologies that did not experience aqueous alteration, and if it can be compared to asteroids that did not experience a lot of aqueous alteration, for example. That will be very interesting, yeah.
We have time for one last question. Nope, I'm not online. So let's thank again Tania for this nice talk.
Thank you.
And thank you very much for coming.